In this video, we are going to discuss routing protocol for the enterprise. Of Unit 5, designing IP addressing in the network and selecting routing protocol for the subject enterprise network design of B7 semester IT University of Mumbai. In this lecture, we will cover EIGRP, OSPF, Integrated ISIS, summary of interior routing protocol features, selecting an appropriate interior routing protocol, and border gateway protocol, which includes BGP implementation example and external and internal BGP. Protocols vary in their support for many features, including VLSM, summarization, scalability, and fast convergence. There is no best protocol. The choice depends on many factors. So, in this lecture, we will discuss the most common routing protocol for use within the enterprise, evaluation their stability, suitability for given network requirement. So, first we will discuss EIGRP. EIGRP is a Cisco proprietary protocol for routing IP version 4. EIGRP can also be configured for routing IP version 6, Inter-Network Packet Exchange, IPX. IPX is a special kind of protocol, okay, and Apple Talk Traffic. EIGRP is an enhanced version of IGRP, which is pure distance vector protocol. So this is pure distance vector protocol. However, is a hybrid routing protocol. It is a distance vector protocol with additional link state protocol features. So EIGRP features includes, first thing, it uses triggered update. EIGRP has no periodic update. Then it uses a topology table to keep all route received from its neighbors, not only the best route. Okay, so it keeps all the record of routes, establishing adjacencies with the neighboring routers using Hello protocol. Use multicast rather than broadcast for communication. It supports VLSM. What is VLSM? Variable length subnet masking. Support manual route summarization. EIGRP summarizes on major network boundaries by default, but this feature can be turned off, and summarization can be configured at any point in the network. It can be used to create hierarchical structured large networks, and it supports unequal cost load balancing. Routers are propagated in EIGRP in a distance vector manner from neighbor to neighbor, and only the best route are sent onwards. The router that runs EIGRP does not have a complete view of network because it sees only the routes it receives from its neighbors. In contrast with a pure link state protocol like OSPF and ISIS, all routers in the same area have identical information and therefore have a complete view of the area and its link state. As you know that the default EIGRP matrix calculation uses the minimum bandwidth and cumulative delay of the path. Other parameters can also be used in the calculation, including worst reliability between source and destination and worst loading on a link between source and destination. So it is very important to note that the maximum transmission unit and hop count are carried in EIGRP routing updates but are not used in metric calculation. So let us now discuss some terminology associated with EIGRP. First thing is neighbor table. The EIGRP routers use hello packet. Okay, it uses hello packet to discover neighbors. When a router discovers and forms an adjacency with a new neighbor, it includes the neighbor's address and the interface through which it can be reached in an entry in the neighbor table. This table is completed and compatible with OSPF's neighbor table or adjacency database. It serves the same purpose, which is to ensure bidirectional communication between each of the directly connected neighbors. So it ensures the bidirectional communication. Okay. EIGRP keeps a neighbor table for each supported network protocol. Now come to topology table. This is neighbor table, information about all the neighbors using hello protocol and maintains the bidirectional communication. Now come to topology table. When a router dynamically discovers a new neighbor, it sends an update. Okay. Whenever it discovers new neighbor. Okay. So it sends an update about the routers it knows to its new neighbor and receives the same from the new neighbor. These updates populate the topology table, okay, because it modifies the topology. The topology table contains all destination advertised by neighboring routers. In other words, you can also say that each router stores its neighbor's routing table in its EIGRP topology table. If neighbor is advertising a destination, it must using the route to forward packet. This route must be strictly followed by the distance vector protocol. An EIGRP router maintains a topology table for each network protocol configured. Then come to advertised distance or AD and feasible distance or FD. Okay. So EIGRP uses the diffusing update algorithm. Which algorithm? Diffusing update algorithm. Dual. Fine. Dual uses distance information known as metric or cost. It uses distance information and known as metric or cost. Fine. To select efficient loop free path, the lowest cost route is calculated by adding the cost between the next hop router and destination, referred to as advertised distance, to the cost between the local router and next hop router. The sum of these costs is referred to as the feasible distance. Okay. A successor, also called current successor, is a neighboring router that has low cost path to a destination, the lowest FD, okay, lowest feasible distance, lowest feasible distance, guaranteed not to be part of routing loop. Successors are offered to the routing table, be used to forward packets. Multiple successor can exist if they have the same FD. Now come to routing table. The routing table holds the best route to each destination and is used to forward packets. Successor routes are offered to the routing table. The router maintains one routing table for each network protocols. Then come to feasible successor. Along with keeping least cost path, dual, that is, what is dual? This is diffusing update algorithm. Okay. So dual is diffusing update algorithm. Okay. So now come to feasible successor. Along with keeping low cost path, dual keeps backup path to each destination. The next hop router for backup path is called the feasible successor. To qualify a feasible successor, a next hop router must have an AD, that is advertised distance, less than the FD. Okay. If AD is less than FD of current successor route, or you can say a feasible successor is neighbor that is closer to the destination, but it is not in the least cost path and therefore it is not used to forward data. Feasible successors are selected on the same time as successors but are kept only in topology table. The topology table can maintain multiple feasible successor for a destination. If a route via successor becomes invalid because of topology change, or if a neighbor changes the matrix, dual checks the feasible successor to destination. If a feasible successor is found, dual uses it, thereby avoiding a recomputation of root. If no suitable feasible successor exists, a recomputation must occur to determine the new successor. Although recomputation is not processor intensive, it affects convergence time, so it is advantageous to avoid unnecessary recomputation. Let us now discuss some of the characteristics of EIGRP. First is fast convergence. Convergence is a sort of synchronization. One advantage of EIGRP is fast convergence, dual root calculation mechanism. This mechanism allows backup root, the feasible successor, to kept in the topology table for use if the primary root fails. Because this process occurs locally on router, the switchover to a backup root, if one exists, is immediate and does not involve action in any other router. Then come to scalability. Okay. Although the fast convergence, the ability to manually summarize also improve scalability. EIGRP summarizes roots on classful network boundaries by default. Okay, classful network boundaries. So this is one thing you must remember. Automatic summarization can be turned off and manual summarization can be configured at any point in the network, improving scalability and network performance because of routing protocol uses fewer resources. Now come to use of VLSM. VLSM is, what is VLSM? Very large scale word. No, it's not VLSM. It is variable length subnet masking. Okay. If we are using classful network, then it is not VLSM, it is FLSM, fixed length subnet masking, and if we use classless, then it will be variable length subnet masking. Fine. So because the EIGRP is a classless routing protocol, it sends subnet mask information in its routing update and therefore supports VLSM. So this is the reason why it supports VLSM. But in case of improved scalability, it works in the classful network boundaries also. Fine. Now come to reduced bandwidth uses. So there is concept of NBMA network. Because EIGRP does not spend periodic routing update as other distance vector protocol do, it uses less bandwidth, particularly in large network that have large number of routes. On the other hand, EIGRP uses Hello protocol to establish and maintain adjacencies with its neighbor. If many neighbors are reachable over the same physical link, as might be case of an NBMA network, and Hello protocol might create significant routing traffic overhead. Therefore, the network must design appropriately to take advantage of EIGRP bandwidth. So as you know that it is not using or it is not updating the vector constantly or periodic update. It only updates whenever a trigger fires. Okay. Now come to multiple network layer protocol support. EIGRP supports multiple network layer protocols through protocol dependent module, that is PDM. PDM includes support for IP version 4, IP version 6, IPX and AppleTalk. The IPX and AppleTalk are the proprietary protocol and traditionally used with network. IPX is very similar protocol to IP, okay, but it is old protocol. So EIGRP is a Cisco's proprietary protocol that can pass protocol information only with licensed devices. So this EIGRP, this is Cisco's protocol. Okay, you must remember this. It is proprietary protocol and it can be used with licensed devices only. OSPF is a standardized protocol for routing IP version 4 developed in 1988 by Internet Engineering Task Force to replace RIP in larger and more diverse media networks. In 1998, minor changes in OSPF version 2 address some of the OSPF version 1's problem while maintaining full backward compatibility. So OSPF is described in this RFC 2328 documentation, OSPF version 2.0. OSPF was developed for use of large scalable network in which RIP's inherent limitation failed to satisfy requirement. OSPF is superior. OSPF is superior to RIP in all aspects, including it converges much faster. It supports VLSM manual summarization and hierarchical structure. It improves metric calculation for best path selection. It does not have hop count limitation. As an inception, OSPF supports the largest network. Okay, so these are the things which makes it superior than previous protocol. Now come to OSPF hierarchical design. OSPF was developed by a large network. Its implementation requires proper design and planning. This is especially important for network with 50 or more routers. Okay, if the routers are greater than 50 or equals to 50, then we need to be careful about its design. The concept of multiple separate areas inside one domain, or AS, was implemented in OSPF to reduce the amount of routing traffic and make network more scalable. In OSPF, there must always be one backbone area, that is area 0. Okay, this is our backbone area. Then to which all other network areas must be directly attached. A router is a member of OSPF area when at least one of the interfaces operates in that area. Routers that reside on boundaries between the backbone and non-backbone area is called area border routers. So this is our area border router. Okay, it is between non-backbone area and backbone area. Now, and have at least one interface in each area. The boundary between the area is within the ABR itself. Okay, traffic sent from non-backbone area to another always crosses the backbone. Like in this figure, the area 1, this is our area 1, must forward traffic from area 1 destined for area 2 into backbone. The area 2 ABR receives the traffic from backbone and forward it to the appropriate destination in area 2. So this is things associated with hierarchical design. You might encounter different terminologies in various OSPF tables. Okay, so these terminology include OSPF neighbor table, that is equals to adjacency database. Then OSPF topology table is equals to OSPF topology database, or LSDB, routing table or forwarding table. These are analogous. Now come to characteristics of OSPF. OSPF is a link state protocol. First of all, it is link state protocol. Okay, that has the characteristics like fast convergence. In previous protocol, fast convergence is also there. OSPF achieves the fast convergence times using triggered link state update. Okay, this also follows triggered, not periodic. Include one or more link statement, state advertisement, that is LSA. LSS describe the state of link on a specific routers and are propagated unchanged within an area. Therefore, all routers in the same area have identical topology tables. Each router has complete view of all link and device in the area. Depending on the type of LSA, These are usually changed by ABRs when they cross into another area. ABR is area border router. So when OSPF topology table is fully populated, the SPF algorithm or shortest path finding algorithm calculates the shortest path to the destination network. Triggered updates and metric calculation based on cost of a specific link ensure quick selection of the shortest path towards the destination. By default, the OSPF link cost value is inversely proportional to the link bandwidth. Okay, so this OSPF link cost is inversely proportional to the bandwidth. By default, the cost in Cisco routers is calculated using formula 100 Mbps divided by bandwidth in Mbps. Okay, 100 Mbps divided by the bandwidth in Mbps. Like 64 kbps link has cost of 1562. Okay, if 64 kbps link has cost of 1564 and T1 link has cost of 64. However, this formula is based on maximum bandwidth of 100 Mbps, which result in cost of 1. If the network includes faster link, the cost formula can be recalibrated. So already we have seen numerical in previous lecture related with this. Then come to very good scalability. Okay, this is another characteristic. OSPF's multiple area structure provide good scalability. However, OSPF's strict area implementation rules require proper design to support other scalability features such as manual summarization of routes in ABRs and ASBRs, stub areas, totally stubby areas, and not too stubby areas. The totally stubby and not to stub areas features for non-backbone areas decreases the amount of link state uh, advertisement traffic from backbone area, that is 0, into non-backbone area, and they are uh, already given in different literatures. This allows low-end routers to run in network's peripheral area because fewer LSAs means smaller OSPF topology table, less OSPF memory uses, and lower CPU uses in stub area routers. So this is one thing. Now come to use of VLSM. VLSM, because OSPF is classless routing protocol, it supports VLSM to achieve better use of IP address space. Then come to reduce bandwidth uses. Along with the area structure, the use of triggered not periodic update and manual summarization reduces the bandwidth uses by OSPF by limiting the volume of link state update propagation. Already know that OSPF does send update every 30 minutes. Okay, update every 30 minutes. Now come to OSPF area type. First area is standard area. This default area accept link updates, route summarization, and external routes. Backbone area or transit area. Okay, transit, like in airport also transit areas are there. So this is the responsible for any traffic from any non-backbone area to non-backbone area, and AS is the autonomous system. So backbone area or transit area, the backbone area, area 0, is central entity to which all other areas connect to exchange and route information. The OSPF backbone has all the properties of standard OSPF area. Now come to stub area. This area does not accept information about routers external to autonomous systems such as routers or non-OSPF sources. If routers need to route to network outside to autonomous system, they use default route including indicated as 0.0.0.0. Okay, so 0.0.0.0 stub areas cannot contain ASBRs except the ABRs may also be ASBRs. Using a stub area reduces the size of routing table inside the area. Okay, now come to totally stubby area. Okay, totally stubby area is a Cisco specific feature that further reduces the number of routes in the routing table inside the area. This area does not accept external autonomous system routers or summary routes from other areas internal to the autonomous system. If a router has to send a packet to network external to the area, it sends the packet using default route. Totally stubby areas cannot contain ASBRs except that the ABRs may also be ASBRs. Now come to NSSA. NSSA is the what is NSSA? Already discussed. Not to stubby areas. Okay, not to stubby areas. Not to need, not so stubby areas. Fine, NSSA. This area offers benefits similar to those of stub area. However, NSSA allows ASBRs, which is against the rule in stub area. Totally stubby NSSA, although it sounds like a very strange name, in Cisco specific feature that further reduces the size of routing tables inside the NSSA. So this is all about OSPF. Integrated ISIS. So it is a very special protocol and it was developed by Digital Equipment Corporation, DEC. Okay, so this is the proprietary protocol of DEC and as the dynamic link state routing protocol for open system interconnection protocol suite, OSI protocol suite. The OSI suite uses connectionless network service CLNS to provide connectionless delivery of data and the actual layer 3 protocol in connectionless network protocol, that is CLNP. CLNP is the OSI suite solution for the connectionless delivery of data. Each and everything is connectionless. Okay, connectionless delivery, connectionless services. It is very similar to IP in the TCP/IP suite. ISIS uses CLNS addresses to identify the routers and build the LSDB. So, link state database, LSDBs. So, what is the terminology associated with this? Connectionless network protocol. Connectionless network protocol. So, this is CLNP. Okay, uh, CLNP or connectionless network protocol. If we use connectionless network services, then it is CLNS and so on. Fine. ISIS was adopted to the IP environment because IP is used on internet, and this extended version of ISIS is for mixed OSI and pre-IP version 4 environment. It is called integrated ISIS. Integrated ISIS tags CLNP routers with information on IP network and subnets. One version of ISIS, integrated ISIS, supports IP version 6. Okay, there is one version associated with this. Even if ISIS or integrated ISIS is used only for routing IP, and not CLNMP. OSI protocol are used to form the neighbor relationship between the routers. Therefore, for integrated ISIS to work, CLNS addresses must still be assigned to area. This proves to be major disadvantage when implementing integrated ISIS because OSI and CLNS knowledge is not widespread in the enterprise network community. Therefore, integrated ISIS is not recommended as an enterprise routing protocol. It is included here for completeness. Okay, so we have described here only for knowledge of this protocol. Whenever some vendor says that we are providing the services based on CLNMP, so better to know what is CLNMP, and on the basis of your knowledge you are able to compare it with some other protocol. If integrated ISIS is not good for you, then discard it, and most of the time we are not interested in integrated ISIS protocol. Integrated ISIS terminologies. There are different terminologies associated with this. ISO specification call routers intermediate system. Okay, ISO specification called routers the intermediate system. Terminologies. Router is intermediate system. Thus, ISIS is a router-to-router protocol allowing routers to communicate with other router. ISIS routing takes place at two levels with an AS autonomous system level 1 and level 2. Okay, so there are two levels, level 1 and level 2. Level 1 routing occurs within ISIS area and responsible for routing inside an area. All devices in L1 routing area have the same area address. Routing within area is accomplished by looking at the locally significant address portion known as system ID. System ID. Okay, and choosing the lower cost path. L2 routing occurs between ISIS areas. L2 routers learn the location of L1 routing areas and build an inter-area routing table. L2 routers use the destination area address to route traffic using lowest cost path. Therefore, ISIS supports two routing levels. First is L1. L1 build a common topology of system IDs in the local area and route traffic within the area using the lowest cost path. Then L2 exchange prefix information, that is area addresses between areas, and routers traffic to an area using lowest cost path. To support two routing levels, ISIS defines three type of routers. Okay, so there are three type of routers. First is L1. Router use link state protocol. It uses link state protocol to learn about path within the area to which they connect, and this is known as intra area. Within the area means inside that area, this uses link state protocol, and this is known as L1. Fine. Now come to L2 routers use LSP, that is link state protocol, to learn about path among areas. Means between two areas it is used, and this is inter area. Then third is level 1 slash level 2. Both the area are there. Routers learn about path both within and between areas. L1 slash L2 routers are equivalent to ABRs in OSPF. Fine. Now area border routers. Okay, ABR. Now come to this particular figure. It shows the three type of area. In area 2, L1 slash L2 is there. Here in area 2, L2 means inter area. In area 4, both L1 slash L2 and L1 slash L2 and L1. This is the topology. So the path of connected L2 and L1/L2 router is called backbone. Okay, so this is called backbone. All areas and backbone must be contiguous. ISIS area boundaries fall on the links, not within the router. Each ISIS router belongs to exactly one area. Neighboring routers learn that they are in the same different areas and negotiate appropriate adjacencies L1, L2 or both. Changing level 1 router into level 1, level 2 or level 2 routers can easily expand the integrated ISIS backbone. In comparison, uh, in OSPF, entire area must be numbered to achieve this. Now come to characteristics of ISIS, integrated ISIS. It is a popular IP routing protocol in ISP industry. The simplicity and stability of ISIS make it robust in large internetworks. Integrated ISIS characteristics include VLSM support. So this is the third protocol in line which supports VLSM. If it supports VLSM, then this protocol is classless. Fine. Then come to fast convergence. This is also in line. Similar to OSPF, integrated ISIS owes its fast convergence characteristic to its links state operation, including flooding of triggered link state update. Another feature that guarantees fast convergence and less CPU usage is the partial route calculation. Although integrated ISIS uses the same algorithm as OSPF for both best path calculation, the full SPF calculation is initially performed by network startup only. When IP subnet information changes, only a PRC, that is partial route calculation for the subnet in question run on routers. This saves router resources and enables faster calculation. A full SPF calculation must be run for each OSPF change. Then excellent stability. Integrated ISIS is more scalable and flexible than OSPF. ISIS backbone area design is not as strict as OSPF, thereby allowing for easily backbone extension. Then reduce bandwidth uses. Triggered update and absence of periodic update. Whenever we are talking about reduced bandwidth, it means triggered. Okay, it is triggered update, and periodic update is not there. Fine. So triggered updates and absence of periodic update ensure less bandwidth is used for routing information. Integrated ISIS offers inherent support for LAN and point-to-point environment only, whereas NBMA point-to-point multi-point environment support is not included. In NBMA environment, point-to-point links sub-interface must be established for correct integrated ISIS configuration or operation. NBMA. One disadvantage of ISIS is its close association with OSI world. Because of few network administrators have adequate knowledge of OSI addressing and operation, implementation of integrated ISIS might be difficult. So this is a summarized view of interior routing protocol features. There is no best or worst protocol. The decision about which routing protocol to implement or whether multiple routing protocols should indeed be implemented in a network can be made only after you carefully consider the design goals and examine the network's physical topology in detail. So in this particular table, it summarizes some characteristics of IP routing protocol. Okay, like RIP1, RIP2, IGRP, and EIGRP, OSPF, and ISIS. Actually, IGRP protocol is no longer supported by Cisco iOS release 12.3. It is included in this table for completeness. Now come to EIGRP protocol. It is an advanced distance vector protocol with some characteristics also found in link state protocol. Okay, and then come to VLSM, so only FLSM is supported in some cases where we use classful. Okay, so classful is support of FLSM, fixed length subnet masking. This is traditional IP address mode. Now come to feature like distance vector is supported by all the protocols except OSPF and ISIS. Link state, if either the protocol is link state or distance vector, so these protocol will not support the features associated with link state. Only OSPF and ISIS is supporting the link state. Similarly, hierarchical topology required OSPF and ISIS. Hierarchical topology supports EIGRP. Okay. Flat topology supports distance vector protocols only. So whatever distance vector protocols are there, like RIP version 1, 2, IGRP and EIGRP. Classless, if we talk about classless, it means it supports CIDR, classless inter-domain routing. So it is supported by RIP version 2 already seen, and EIGRP, OSPF and ISIS. Okay, RIP version 2 is extension of RIP version 1 to support this classlessness. Then classful is supported by version 1 IGRP, and none other protocol will support the classful. Performs automatic route summarization. So all the link distance vector protocol supports the automatic route summarization. Manual route summarization support is by all the protocols which supports link state, including EIGRP and RIP version 2. Multi-access LAN support. It is supported by every protocol. Point-to-point support is also done with the help of all the listed protocol. NBMA. This is non-broadcast multiple access point-to-point protocol support. So with OSPF and EIGR. So this table is very helpful. Whatever you want, on the basis of this, you can get the result. Now come to the point, selecting an appropriate protocol, interior routing protocol. So the selection of routing protocol is based on the design goals and physical topology of the network. Both EIGRP and OSPF are recommended as enterprise routing protocol. So this table is very helpful. Like if the parameters and required network parameters are yours. So like the parameter size of network, whether it is small, medium, large, very large. So in case of OSPF, it supports OSPF, means OSPF supports large network, and EIGRP also support large network. Speed of convergence. So what is the degree of synchronization you want? So high degree of synchronization is there with OSPF, and EIGRP supports very high degree of support. Scalability, both supports scalability. Support for VLSM, already seen in previous table that both support VLSM. Support for mixed vendor devices, yes. EIGRP as already discussed in EIGRP slide, that it does not support non-mixed vendor devices because this is Cisco's proprietary protocol. Multiple network layer protocol support. So multiple network layer protocol support is done with the help of EIGRP, and it is not done with the help of OSPF. So whenever we are going to a large network with high degree of convergence and also support of scalability and VLSM and multiple network layer, then we choose EIGRP, and with or without the means with mixed vendor devices. When to choose EIGRP? Okay, so on the basis of this, we can decide. There are two questions: when to choose EIGRP and when to choose OSPF. EIGRP is Cisco's proprietary hybrid protocol that incorporates the best aspect of distance vector and link state features. EIGRP keeps a topology table. It does not perform periodic route updates, and it does perform triggered update. Therefore, it is well suited to almost all environment, including LAN, point-to-point, and NBMA, non-broadcast multiple access. EIGRP split horizon functionality can be disabled in NVMe environment. EIGRP is not suitable for dial-up environment because it must maintain in a neighbor relationship using periodic hello packets. Sending these packets would mean that the dial-up connection would have to stay up all the time. And whenever we are talking about OSPF is a standard based link state protocol that is based on SPF algorithm for best path calculation. OSPF was initially designed for network of point-to-point links and was later adopted by operation in LAN and NBMA environment. OSPF can be used on dial-up link with the OSPF demand circuit feature, which suppresses the hello protocol. The OSPF hierarchical area requirement improves design constraints in larger network. One backbone area is required and all non-backbone area must be directly attached to that backbone area. Expansion of the backbone area can cause design issues because the backbone area must remain contiguous. So this is the thing. On the basis of previous table and this table, we can decide that EIGRP, whether you want to use EIGRP or whether you want to use OSPF. Fine. So whatever parameters you are interested, like large network, you are interested, high is and scalability is required, support of VLSM is required, and mixed vendor is not required, and multiple network is required. Then what will be your choice? So you won't be able to select EIGRP, or you are able to select the EIGRP, but you need to compromise with multiple network layer protocol support. If the answer is no, then you can support. Again, there is problem. We need two compromises. If we use yes or no, okay. Based on this requirement, EIGRP is recommended. Fine. This next line of protocol is border gateway protocol. So what is border gateway protocol? BGP is an EGP that is primarily used to interconnect autonomous system. BGP is successor to the EGP. The exterior gateway protocol, because EGP is obsolete, BGP is currently the only EGP in use. BGP4 is the latest version of BGP. It is defined in RFC 4271, a border gateway protocol. Okay, so this is defined here. It is very important that RFC, in this particular RFC, the classic definition of AS is a set of routers used under a single technical administration using an interior gateway protocol and common matrix to determine how to route packets within the AS, and using an inter-AS routing protocol to determine how to route packets to other autonomous systems. So this is defined in RFC 4271. Extension to BGP4 is known as BGP4 plus, have been defined to support multiple protocols including IP version 6. These multi-protocol extension of BGP are defined in RFC 2858, multi-protocol extension of BGP4. The main goal of BGP is to provide an inter-domain routing system that guarantees the loop-free exchange of routing information between autonomous systems. BGP routers exchange information about path to destination network. BGP does not look at the speed to determine the best path. Rather, BGP is policy-based routing protocol that allows an AS to control traffic flow by using multiple BGP attributes. Routers running BGP exchange network reachability information called path vectors or attributes, including a list of full path of BGP AS numbers that routers should take to reach a destination network. BGP is therefore also called a path vector routing protocol. PVRP, path vector routing protocol. Okay. BGP allows a provider to fully use all its bandwidth by manipulating these path attributes. This AS path information is useful constructing a graph of loop-free autonomous system. It is used to identify routing policies so that restriction on routing behavior can be enforced based on the AS path. Important thing to note is that attributes can be used within AS influence the path that packet takes within the AS and how the packet gets neighboring AS. Some attributes can be used to attempt to influence how a neighboring AS routes its traffic. However, an AS cannot mandate how a neighboring AS routes its traffic. BGP is an autonomous system, and it is the most appropriate when effect of BGP as well as it is understood at least these one of the three things may be there. BGP use an autonomous system and most is most appropriate when the effect of BGP are well understood and at least one of these exists. The first thing is autonomous system has multiple connection to other autonomous system. The AS allows packet to transit through it to reach other autonomous system like it is an ISP. Routing policy and route selection for traffic entering or leaving the AS must be manipulated. BGP implementation requires considerable knowledge. Improper implementation can cause immense damage, especially when neighbors exchange complete BGP internet table, which can have more than 190,000 routes and are growing. So be careful. So this is an example of BGP implementation. Okay, in this figure, BGP is used to interconnect multiple autonomous systems because of multiple connection between autonomous system and need for path manipulation. The use of static routing is excluded. AS6500, not 000, is a multi-home to three ISPs: AS6550, 64600 and 65250 ISP. Okay, so this is the example of BGP implementation. Now come to external and internal BGP. BGP uses TCP to communicate. Any two routers that have formed a TCP connection to exchange BGP routing information, or you can say that a BGP connection are called peers or neighbors. BGP peers can be either internal or external. Okay, so BGP peers can be internal or external. Clear? When BGP is running between routers within one autonomous system is called internal BGP or IBGP. IBGP is run within an autonomous system to exchange BGP information so that all internal BGP speakers have the same BGP routing information about outside autonomous system, and so that this information can be passed to other autonomous system as long as they can reach each other. Routers that run IBGP do not have to directly connected to each other. Static routers or routes, okay, static routes or routes learn from an IGP running within AS provide reachability. When BGP runs between multiple different autonomous system, it is called external BGP. Okay, EBGP. Like this is EBGP, IBGP. Inside one network, this becomes IBGP, and inside two network, two different network, it is known as EBGP. Clear? So this diagram automatically reflects the thing uh, where this BGP is located. So this is external BGP and this is internal BGP. So all routers in the path between IBGP neighbors within autonomous system is called transit path. Okay, this is transit path. And must also be running BGP. These IBGP session must be fully matched. Okay, if one more router is there, then they are also interconnected. IBGP is usually not the only protocol running in the autonomous system. There is usually an IGP running also instead of redistributing the entire internet routing table. Learn via eBGP into IGP or IBGP carries the eBGP routes across the autonomous system. This is necessary because in most cases the eBGP tables are too large for an IGP to handle. Even if eBGP has a small table, the loss of external routes triggering extensive computation in IGP and should be prevented. Other BGP uses include applying policy-based routing within an autonomous system using BGP path attribute, quality of service policy propagation on BGP, which uses IBGP to send common quality of service parameters such as type of service between routers in the network and result in synchronized quality of service policy. Multi-protocol level switching, uh, virtual private network where the multi-protocol version of BGP is used to carry MPLS VPN information. So these are the uses. Okay. Now let us see what is the next topic. So in this lecture we have covered EIGRP, OSPF, integrated ISIS, summary of interior routing protocol, and selecting an appropriate interior routing protocol with extension of EIGRP and OSPF selection, border gateway protocol and its implementation and example. Now, all these protocols are routing protocol for the enterprise. Next video, we will see routing protocol deployment. So thank you very much. Bye bye for now. Have a nice day. Have a nice time.